and welcome to the Road to Genome podcast. I'm your host, Helen Bethell, Genetic Counsellor and Workforce Development and Education Lead for the North Eastern Yorkshire Genomic Medicine Service, or GMS. Today, I'm delighted to be joined by Professor Sir John Byrne, Honorary Consultant Clinical Geneticist at Newcastle Hospitals, to discuss his own road to genomics and his very distinguished career. Hi, John.
Hi, nice to see you, Helen.
Yeah, you too. It's a real pleasure to be talking to you today, John, as someone that I've fleetingly worked alongside at points, but also as someone who has had such a distinguished career. So the rumours are that you are retiring. However, trying to book into your diary for today, it seems that you're busier than ever. So of all the hats that you've worn over the years, which ones are the ones that you're currently still wearing?
Well, I've just been revalidated as a doctor for another 5 years.
Great.
So when people say, what do you do? I think doctor is what I would always say first.
Mm-hmm.
But obviously I became a professor 30 years ago. And so I'm an academic as well. And I have a bunch of hats still. I just stopped being chair of the hospital, which was nice to be finished with because it's quite demanding.
Mm-hmm.
But I am still an honorary consultant. I've just reverted to that. I had to stop being an honorary consultant while I was the chair.
Okay.
I was technically a specialist.
Mm-hmm.
And I'm now part-time in the university, but still running my research team. I do a little bit of teaching, not very much. I chair a biotech company, which we launched here about 12 years ago, called Quantum DX, which is now going very well. And we're making point-of-care battery-operated DNA testing devices so we can take them out into the field. And there's some very exciting developments on that front.
Yeah.
I'm currently vice president of the Human Genome Organization and have been helping to restructure that and merge it with a UNESCO charity that I lead called Global Variome, which tries to gather variant information about widespread populations around the world. So yes, so there's quite a few things sort of still bubbling along.
Doesn't sound like a quiet retirement. It all sounds very, very interesting. So where did this all start then? So when you were maybe at school or as a child, what job was it you aspired to do, or did you always know that this was for you?
No, on the contrary, I grew up in a pit village in southwest Durham, which is a very poor area of a sort of ex-mining area. And I went to grammar school and I was originally going to be a chemical engineer based on the profound discussion with my father as we drove past ICI. And I was very impressed by all the lights and pipes. And I said, I'll be one of those. And then I realized that in the small grammar school, I had to choose between biology and maths, and I could do both, but I enjoyed biology. And no one mentioned that I wouldn't be allowed to be an engineer without a maths A level.
Yeah.
So it was a very well-planned career. And then the biology teacher said, well, why don't you do medicine? And to be honest, it had never crossed my mind because back in the 1960s, it was still very much seen as a sort of an hereditary trait, that doctors were mostly the sons of doctors and they were mostly male. And so I said, well, okay, I'll give it a go. And I was offered a place here in Newcastle and did well in my O-levels. So I only needed 3 C's to get in, which shows how far back it was. And I arrived at Newcastle wearing my 3-piece suit because I didn't know what you wore at university. I'd never spoken to anybody from a university before. So it took me a while to find my feet.
Yeah.
But in fact, I'd already been, sort of, if you like, infected by genetics because when I was 17, our school biology teacher took us to a lecture at Lumley Castle by an academic from Oxford explaining the genetic code.
Wow.
Now, this was just at the beginning of the realization that, we could crack the code and know that which 3 letters meant which amino acid. And the thing that really stuck in my mind was that it was such a nice, simple concept, but also the biology teacher couldn't understand it. So I had to explain it to him again on the way back to school. Yeah. And that stuck with me. And then when I got to medical school, for the first time in my life, I tried hard because I was feeling a little bit, insecure among all these doctors' sons. And I tried a bit too hard and ended up sort of, almost top of the year and got offered a degree. So my dad at the time had finally started doing pretty well, recycling pit heaps.
Right.
In my spare time, I used to sell coal door to door.
Wow.
And so I knew we had enough money to cover me doing an extra year. So I took the year out and I thought I'd do genetics. So I got my genetics degree in 1973.
Yeah.
And then I went back into medicine, and then I realized that in the land of the blind, the one-eyed man is king. So I started explaining on ward rounds all about genes and genetics and DNA. And so I then went to Johns Hopkins and worked for Victor McCusick, who wrote the big textbook, in my elective. And I came back, and my dad was a kind of small business entrepreneur. And it was essentially an entrepreneurial decision. I realized this was a gap in the market.
Yeah.
That nobody in medicine seemed to have noticed that DNA was coming down the track.
Yeah.
So I announced in 1974 as a medical student that I would be the first clinical geneticist in the North.
Fantastic.
And they all said, "What's a clinical geneticist?" And I said, "Well, it'll be there by the time I get there." And it was. In those days, you had to prove you could work hard.
Mm-hmm.
So I did all of the on-call 1 and 2, RMO, medicine, pediatrics, and all of that for 5 years. And then I went down to Great Ormond Street to the MRC unit and worked there for nearly 4 years, and then came back as the first consultant in 1984.
Fantastic.
So, and I always wanted to come back to Newcastle because we had this kind of captive population of 3 million people who don't move much. And from a genetics point of view, it was an ideal setting.
Yeah.
But also I came back to the department I'd done my degree in.
Yeah.
So I kind of, had a base to operate from, and we lived in a little tourist house on Claremont Road, as you may know. So that's where it began, and we just started to expand from there. It took a while to take off, and I managed to have clinics all over the region. I, for 20 years, did a clinic in Whitehaven, driving there for 2 hours, do a clinic, drive back. So I put the miles in. But we just started to outgrow our space. And also, of course, the whole thing was taking off. So we were becoming really quite powerful in terms of our diagnostics. And we, in fact, were, outperforming the main academic units in the university. So I got lifted out and moved into the university. And then basically we built the Centre for Life with the Millennium Landmark Project, and just here we are,
That's
a few decades on, still,
So a real trailblazer right from the outset.
Yes, and it was really, as I say, it was a kind of entrepreneurial thing as much as anything.
Yeah.
It was just a gap in the market. I mean, if I was coming now, I'd probably be thinking more about IT and artificial intelligence. And, it's now an established specialty, but no one knew how to spell it. In fact, when I wrote the first contract, someone auto-corrected it to geriatrics.
Really?
They didn't even know what genetics stood for.
Yeah.
It was fun to be in at the start. And of course, it also meant that you could cover the whole spectrum of genetics.
Yeah.
Whereas now it's become so big, you have to subspecialize. And so I've kind of followed the novelty line and kept slightly changing horse over the years.
Yeah.
But still always basically stuck with genetics as my core belief.
Yeah. I mean, it's amazing to hear the story, John. Obviously, I know the person, so it's lovely to hear your story behind it. And as I say, it sounds very much like you're a trailblazer, and it's fantastic that you obviously, similar to me, loved genetics from that first moment of learning it. And for me, it was that understanding it right to the very smallest molecules. It didn't get any smaller than that. And so I could start building in my understanding of it, because that's where it all started. But what's lovely is that you've had the passion and the drive to take a discipline that wasn't really existing as such, but had your interest, and actually took it and drove it forward, and was so instrumental in establishing what we have today in terms of
I think what was interesting was that up until 1970, geneticists were a kind of ragbag of interesting different people. And it was only in the early 1980s that really the doctors arrived. So Dido and I, Robin Winter, myself, Peter Farndon, we were all medically trained people who were bringing genetics into mainstream medicine. And of course, we were also very lucky. We caught a wave in the sense that the whole Genome Project, I was there when the very first DNA diagnostic test was done in this country.
Wow.
And so being there at the ground level meant you could actually ride with it. And of course, we went through a golden age almost, where we were literally sort of diagnosing a new syndrome every week.
Yeah.
And as the gene markers became more and more easy to use, we started to find the genes, and first of all, it was the hard ones like Duchenne muscular dystrophy and Huntington's disease. But pretty soon, everything became possible.
Yeah.
And so it was a sort of Wild West in a sense. It was that sort of sense that you could go and discover new territory.
Yeah.
Whereas now it's become industrialized.
Yeah.
So it has actually changed dramatically, but probably for the better, in the sense that we used to have people hanging around for years waiting for us to work out what was going on.
Yeah.
And now it becomes a relatively straightforward exercise in many cases to find the genes. So it has changed for the better.
Out of interest, what was the first gene test that was done?
It was for sickle cell. So so we already knew from the protein chemists that, it was the 17th base along from the start of the gene that had gone one letter switch. And it happened that the guys working on restriction enzymes, which, as you know, were identified from bacteria, and they were called restriction enzymes because they cut DNA up to destroy the enemy. And it happened that we had a restriction enzyme that actually hit the spot where sickle cell mutation occurred. And it's always the same place. So basically, it was a simple enzyme digestion, whether or not you got two bands or two or one. So you didn't actually need to sequence the DNA. So that was the very first breakthrough. And then the very first linkage was actually Shomi, who we hired in. Shomi Bhattacharya came here from Edinburgh, and he was the first person to get a clinically useful diagnostic linkage to X-linked retinitis pigmentosa. So we hired him down here with a grant from the Muscular Dystrophy Association, and we set up the very beginning, the very first DNA lab in the region. In fact, one of the first in the country. My brother-in-law and I built it in the first floor of an Edwardian tourist house. And he was a joiner, and he kind of put all the units in from MFI, and I painted the ceiling because it was quite high. And so it was really making it up as we went along.
And built it from literally almost ground up. But if it was
in a bedroom. The regional diagnostic laboratory was a bedroom.
Yeah, fantastic. So you mentioned about if you were to kind of do your career again, you would think about maybe if you're doing it in today's age, you would think about other disciplines like AI and bioinformatics. So if you could go back to you in the time frame that you were in, what advice would you give to your younger self or someone else starting out?
First of all, I would have tried harder to be a scientist. I mean, I was a good doctor, I think, but I never really had, I did a science degree, but I never had the application to be good in the lab. Which probably was good in a way because it meant that I sort of always floated a slightly one step removed from it. But it would have been nice to get a bit more hands-on with the lab work. But fundamentally, my biggest weakness, which has also weirdly been a strength, is I'm a great starter and a terrible finisher.
Really?
So I realized after a few years that the only way to succeed was to attach myself to really good finishers and inspire them to start. But what that meant was you could come up with a project and then kind of give it away and move on to another project. So that was beneficial for my career because it meant I sort of, published all over the place. But in truth, it would have been nice to see some of those stories through. And one or two of the stories, it took me forever to finish them. I mean, the most dramatic example was neuroferritinopathy, a disease we invented in Cumbria, which turned out to be an incredibly rare condition. And I met this family in the clinic in Carlisle, and they come with their mother. They said she had Huntington's disease. She told me all their dates of birth, and I said, "Look, I don't know the dates of birth of my family. How can you possibly have Huntington's disease if people with dementia don't remember everyone's birth dates?" So I realized it was a new condition. Then I found a cousin who had what's called tardive dyskinesia, funny tongue movements. So I brought them both into the hospital, scanned them, and they both had these weird holes in their basal ganglia. And then we realized we were onto a new condition. And that was in 1990, and I presented it to the Clinical Genetics Society, and it took us a full decade to actually solve that. Now, it was partly because we didn't quite have enough linkage data, but to be honest, it was also partly that I was always too busy doing something else, and we should have finished that story a lot sooner. And indeed, it's still rolling. So Patrick Chinnery, who joined us in the quest, who now leads the MRC, he's just finally, we're getting the trial running because the condition leads to an accumulation of iron in the basal ganglia. And we demonstrated it starts from early life, but it doesn't actually cause the basal ganglia to decline until you're in your 40s and 50s. So the analogy I've used is it's like there's a bin strike and you've got black bin liners in the kitchen and they fill up the kitchen. But for the first little while, you get round it, but eventually nothing can get past them and then the problems start. And what was amazing was that Andy Curtis, having spent years trying to find the gene, we eventually realized it was on chromosome 19, which was a nightmare because it's the most gene-rich chromosome. And then Andy was just looking down this long list of genes and he noticed one called ferritin, and he just happened to have read that people with Parkinson's disease get iron staining in the brain. He said, "Oh, the iron, ferritin, we'll try it." And literally in a week we got the gene. So we got our point mutation, and the reason it was so vanishingly rare was that instead of getting a premature stop codon, the change in the gene actually made it get longer. And ferritin is a sort of like a big beach ball type molecule that stores iron. and there are little holes for the iron to get in and out.
Yep.
And if you extend the protein, the holes get blocked.
Okay.
So the iron gets in and can't get back out again.
Yeah.
So at a stroke, we'd moved from not having any idea what it was to actually having the exact cause
and knowing
the biochemistry and actually having potential treatment with iron chelation.
What fantastic.
And there's a trial about to finally start. The important thing about that was that it spanned that decade of explosion in diagnostics, where in the 80s we were so dependent on our clinical skills to say that is Rubinstein-Taby syndrome because I say so.
Yeah.
Then we start to get all of the microdeletion syndromes and things like 22q11 deletion, which were very important. We did a lot of work on. And then gradually by the end of the 90s, almost anything was soluble, and a decade on from that, absolutely, you just sequence it and, you get to the story. And with one rare exception, in fact, which was actually, I have to mention it because it's called Byrne-McEwen syndrome. So it was a condition we described in the early 90s. Yeah. And these kids had no holes in their nose, so they couldn't breathe through their nose, but they had a very unusual face and they looked alike. And I spotted these two brothers, and then Carol McEwen showed a couple of other boys at our dysmorphology group, and I said, I don't know what that is, but it's the same as the one. I don't know what it is.
Yeah.
So we wrote it up. And we tried to crack it. And eventually it transpired that the gene was a spliceosome gene. So basically the spliceosome is what puts your genes together.
Yeah.
And if you break your spliceosome, you're dead because nothing works.
Yep.
And so this was a gene that controlled the spliceosome. And what had happened in this family was that they had one copy of the gene knocked out, and the other copy was downregulated by a deletion in the promoter.
Right.
So we kept sequencing the genes and couldn't find it because the mistake was next door.
Yep.
And it meant that you had a bit of function, so you didn't die, but you just end up with these weird malformations. And in fact, colleagues in Germany and Manchester eventually, they got families, and we eventually got the solution. But I always loved it because that was 2014, and we ended up writing a paper where I was actually an author and in the title. I thought, that's a one-off,
Yeah.
But what was lovely about that was that even the most complex conditions become soluble. And that's what's made our lives both more rewarding but also more challenging because the amount of things we can do now at pace is overwhelming.
Yeah. And I think what I hear you describing is that kind of combination of science and the clinical really coming together. And I think that's what I see certainly, in like the training posts that for genetic counselling now is that, trainees spend a lot of time in the labs and spend time interpreting and what have you. It makes me quite jealous that they've got to do that as part of their training. Like you say,
absolutely.
You've kind of always been on the periphery of the lab and never quite in it.
Yeah.
And I think kind of my career is probably slightly similar. And actually, in our other episode, Jackie Cook commented on how it was the science and the medicine coming together, working with people that has been the passion. And I hear that from the three of us. Yeah, exactly. Yeah. And actually now there is roles for genetic counsellors sitting in labs that are doing that interpretation of the reports for patients. So it's interesting how that science is coming even closer to the work we do.
And it's really important we do that because one of the downsides now is that we're collecting these millions of variants and it becomes very sort of mechanistic. You say, oh, that is a variant of uncertain significance. But if you've got some clinical knowledge, you say, yes, but.
In the picture of the family.
If you look at it in the context of this family and if you look at the gene that it's in, it's the right place. So this is really almost certainly pathogenic.
Yeah.
And that's the work that I do with Human Genome Organization and Global Variome is all about trying to bring together clinical expertise with mechanistic sequencing of DNA.
Data.
Otherwise, we end up throwing a lot of the babies out with the bathwater, and we don't recognize what's of value. So, but I think that we're in a sort of transition zone. And I think what we'll find, especially with AI, is that it'll become better and easier to sort of work out what's real and what isn't. So I think this is a transient period when we'll reach a point where the machine will really tell us the answer really very fast. And that will change. That will make clinical work more interesting because you get an answer to work with.
Yeah.
Just telling people you don't know, as you know, is really tiresome.
Yeah.
And you see people for years and years and years saying, I still don't know, but please come back later.
Yeah, exactly. Yeah. So over your career then, which parts of your role have you found most challenging?
Well, getting things finished, getting my MD finished, so that I could become a professor, which kind of sat on the side of my desk for a very long time.
Yeah.
Leadership of large groups is challenging because this only works if you can get a big crew. And at its peak, the Centre for Life, when I was head of institute and head of the service, we were up at about 800 people on the site. So it becomes a kind of major job managing people. And that's probably always the most difficult thing.
Yeah.
But I think that's a general issue in medicine and academic life, that actually you've got a big crowd of people, but they're all in little subgroups.
Yeah.
So it's actually a lot of little businesses, little specialties in the hospital and little research teams in the university. And I think that's one of the dilemmas that we have, trying to maintain high quality uniform service when it's so dependent on the interaction of so many small components. I don't think there's any answer to that. It's just a continual challenge. And then, I mean, I guess my other big challenge has always been I really like seeing patients and doing clinical work. But as you get drawn into administration and drawn into research, you haven't got the time to do that, which is why I've learned belatedly to kind of narrow down. So I switched. I was one of the first people to switch into cancer genetics because that was clearly a massively growing area in the early 1990s. And I kept that specialty. So I moved away from dysmorphology and fetal medicine and just tried to focus down and then focus further down to the hereditary bowel cancer syndromes so that I could remain expert in one clinical area while running a broader research work.
Too thin and spread. Yeah. So on the flip side, you touched on it there, then which bit of your work have you found the most rewarding?
I think the most rewarding things, first of all, discovery. I mean, actually finding a new disease and finding the gene for it and getting into Nature Genetics was just, off the planet. But at the same time, there's just the satisfaction of solving people's problems. There's a young little girl called Rebecca who had Russell-Silver syndrome. And I cared for her parents when she was born, and then I met her as an adult. And when I stepped down last month as the chair of the hospital, someone sent some nice messages out, and that family said, he was always there for us. And that's kind of warming to think that there are families that I've worked with over the years that still feel like I'm part of their family. The downside of that is you meet them in supermarkets and they walk up to you and they start a conversation which you last were in 12 years ago, like you're supposed to remember who Uncle Fred was, and you learn the skills of sort of trying to extract some information to give you a clue as to exactly which part of my life is this from, So how long has it been now since, and you're sort of trying to re-engage with the family's problem, because of course the lovely thing is you're still kind of a living member of the family, even though you haven't met them for 15 or 20 years or whatever. So that can be challenging, but it's a nice challenge.
Yeah, and I'm sure there's many patients out there that would probably reiterate the same, how amazing you've been as part of their diagnostic journey. That's great. So thinking of your casework then and your kind of work in clinical genetics, can you think of a particular case that has stayed with you throughout your career?
Inevitably, having done clinics, for years, there's huge numbers of them. And some of them are sort of great. So like the one I mentioned about discovering a new disease, that was obviously very exciting. And having the first family to do diagnostics for Lynch syndrome and so on was wonderful. But actually one that really stayed with me was a young lady who was from a Pakistani background, and she had a brother with muscular dystrophy. And I saw her, we were just at the beginning of being able to do molecular testing for Duchenne. And she said, well, I can't have a carrier test and prenatal testing without my family's support. And my dad's in the Middle East. And by pure coincidence, he was in Dubai. And I was actually flying to Dubai the next day. And I said, I'll call and see him. And she seemed completely unfazed by that observation. So I went to see him, and he was a lovely man. And he gave me a very nice gift. But he said, I'm sorry, we spoke to the imam. We can't do that in our family. So I came back to tell her the bad news, but she was remarkably relaxed. And she said, well, if I have a child with muscular dystrophy now, it's not my problem, it's the family's problem. And I thought that was an insight into, genetics, the word means the study of familial traits. And we've slightly lost focus on that. We're so individualistic that we have to remember that there is still this family dimension, and that families are different, and that just because we think it's a good idea doesn't necessarily mean that they'll all agree. And another example of that was the huge Durham family with 35 people got bowel cancer. And yet when we tried to test them for the gene, half of them wouldn't be tested, which seemed to us weird. And Lorraine Cowley did her PhD on this, and because they were scared of being told they had the gene. And what Lorraine found was that they became a kind of underclass. They were a moral underclass because they weren't standing up and being tested. And I think we have to protect people and allow them to not know. And that's the hardest thing in the modern era, because as we move into this sort of industrial sequencing, it will be harder and harder to avoid the knowledge. And so we're still in a position where we're telling people that they have a condition that we can't fix. And they are now going to have to carry that knowledge. And of course, with the new discussions about sequencing newborns, which we wrote a report on 20 years ago, I think we'd never do it, but now we actually are. You have the additional level of what do you tell a child and what do you tell the parents and when do you tell them? And will the child grow up and say, why did my parent get told that? I didn't want them to know that about me. And so we're kind of going to have a challenge of managing that knowledge, the burden of knowledge. And we must never lose sight of the fact that it isn't all good news. Even if you can fix it, just the knowledge that you carry the gene, if your experience of it in the family is bad. I used to use a picture of Dirty Harry in my lectures, where he said, do you feel lucky? And the fact is, if you've had anything go wrong in your family, you don't feel lucky.
No.
So we sit there calmly saying there's only a 5% chance. And then I used to say to people, and I know what you just thought. You thought, knowing my luck, I'll be the 5%. Because you once you've had a bad experience in any aspect of your life, you anticipate it. And whereas we sit in, splendid isolation, never having had the problem and saying, I'm 95% sure it's okay. But that's not good enough for most people. So I think, I digress a little, but I think that young woman making me realize families matter and sharing it with the family is something that to some extent we've lost in our modern society, which adds extra weight to the burden of genomics.
And certainly as a genetic counsellor, my heart sings to hear clinicians describing this and, the importance of that careful counselling, and because obviously that's, ultimately what a genetic counsellor does is in addressing that. And I think, it's great to hear clinicians, and it's great that genomics is being rolled out and expanded, but I think there is a balance, isn't there, and a care that needs to take with it. So we use the terms genomics and genetics interchangeably. How would you define the difference between those two terms?
I spent a long time thinking about this. I did a thing called the Harveyan oration, William Harvey sponsored in the Royal College, and that was sort of the centre of it, because William Bateson made up the word genetics in the early 20th century to describe Mendelian inheritance in humans. And it was about the study of familial traits, not necessarily just Mendelian traits. And that, of course, led to the inborn errors and so on. Genomics is basically the big picture. And it really began at the same time. Thomas Bovary realised that cancers had funny chromosomes and drew pictures of them in 1909. And then, of course, when Lejeune gave us the trisomy testing for Downs, that wasn't a family test, that was a genomic test. So in a sense, the cytogeneticists were always the genomicists looking at the whole thing, whereas we were chasing families and trying to connect the dots. And I think what we're now moving into is an era where genomics is dominated. So now we're just looking at the big picture as a standard of care, and have slightly lost sight of the familial trait dimension and the things run in families. We are less important as geneticists now to finding genes because you can just look at individuals. But we're still going to be important in connecting the knowledge to the family because medicine is all about individuals. And once you've found a genetic disorder, you've then got to manage that in the rest of their relatives. And that's where genetics still retains its relevance. But of course, it's now sitting on the back of genomics in a way that it never did before. We used to be sort of slightly separate from cytogenetics. Now genomics underpins genetics. So it's more powerful, but still different.
And I think that's a fundamental difference that underlines the mainstreaming agenda and the knowledge gap that is out there with with clinicians is that their focus, understandably, from their area of medicine is the person that's sitting in front of them. Whereas in clinical genetics, we're very much about the 360 and those around them. And it's getting clinicians to shift that thinking and, as you say, thinking about all those things that we've touched on about the right not to know and whether it's right for the patient, and it's bringing that into their practice. It's not just another simple diagnostic test.
And we have no choice but to bring them in, because the scale is now way beyond the people who call themselves geneticists. And we were discussing in our last clinical meeting, GPs getting very cross that we wouldn't do alpha-1 antitrypsin carrier testing. But there's millions of them, you know, and you can't manage that kind of carrier testing and large-scale population work. So we have to educate. People have to learn. I used to use the thing, because I grew up watching cowboys on the telly. And there was a thing, I used to say it's the Dodge City model, that the sheriff needs to chase the bandits. So anyone who's got a horse and a rifle is now a deputy sheriff. And so right from the get-go, I used to say, look, if you like inherited stuff and whatever you're interested in, just come join the team, you know, whether it be retinoblastoma or whatever. And I think we need to really make that the norm, that we need to welcome people in into their specialty area and support them to do the job rather than being the ones trying to do it for them, because there's just not enough of us.
Yeah, completely agree. Thank you so much for doing some reflection. So just looking towards the future now. So looking towards the kind of the near future and the maybe even the far ahead future, what do you think are the most exciting developments that are coming?
So I think the most exciting thing always tends to be technological, because ever since that first restriction enzyme sickle cell test, we've been sort of, you know, chasing the dragon. The technology is constantly being pursued. I remember sitting watching Ian Cross do the very first fish analysis, and we saw the very first deletion of chromosome 22 on the screen emerging, like chunk, 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 chunk. So, you know, these moments sort of are dramatic. The same thing's still to come. So one of the things I have a slide which shows all of the things that you miss with an Illumina short read sequencer. And it says at the top whole gene sequencing. Then we talk about rearrangements and methylation and telomeres and all the other stuff. And then the W falls off the whole, because it's basically full of holes. That's going to change. So Evan Eichler is a good friend of mine who runs a big lab in Seattle, and he and I have just been speaking in India together, and he gave an amazing presentation on the combination of PacBio, which is a long read sequencing heavy duty machine, and the Oxford nanopore technique, which is very noisy. As you know, you send the DNA through a hole and read it as it goes through, and you make lots of mistakes, but it can read huge lengths, and it can read methylation. So he actually presented a near perfect whole genome sequence, which was genuinely the whole genome from end to end of the chromosomes, haplotyped, so you knew which one came from which parent, where the rearrangements were, where the deletions and everything was, and even the centromeres. So they've demonstrated, if you look at the methylation across the centromere, that you can see these little dips in the methylation, and almost certainly it's the kinetochores where the chromosomes join together. And looking at a child with Down syndrome, they found that the kinetochore point was different. So it might be that non-disjunction, which we've just always accepted as just a chance event, it may be that we can identify some parents who are susceptible to that because their binding points are slightly wrong. So, I mean, what it tells us is that, I mean, what almost certainly what's going to mean is that we're going to move from doing jigsaws with tiny, tiny pieces that take a year to jigsaws that you could do as a 3-year-old with pieces this big. And you can assemble a genome, you know, and not only that, but also see the vast rearrangements and duplications and deletions that we're missing at the moment. And it'll be like being in a museum and somebody suddenly hitting the lights and you go, oh, wow, you know, look at all this stuff. And that, I think, will be transformational, because I think it will mean that we can get away from so much of the uncertainty and doubt. But how fast we can get to that point is a challenge. And then the other big thing, which I'm involved with UNESCO and Hugo, is how do we take this out to the rest of the world? You know, I mean, going around India and looking at 1 billion people and trying to deliver our quality of genomic care into the whole global population. is really challenging. That's where the work I do with Quantum DX is so exciting, because actually having a multiplex PCR device that'll give you a result in 30 minutes. And I've been talking to one of our gynecologists, Asima, who works on Teesside, but she spends 6 months of the year in India. And she goes up into the tea plantations to look after the women who pick the teas. And she wants our machine to put in a backpack so she can take it up and do HPV testing for cervical cancer.
Incredible.
And so that's sort of taking it to the people, all the people, rather than just the rich few who live in the West. I think that will probably keep me working a while longer.
Yeah, fantastic. Well, John, I can't thank you enough for coming in and talking to us. It's been absolutely inspirational talking to you and just sharing your passion for genomics. It's been great, so thank you very much.
Thank you.
And thanks to you all for listening. Never miss an episode by subscribing to the show on Apple Podcasts, Spotify, or wherever you listen to your podcasts.